Children, here this is the second question that I am going to discuss in Unit 4. The first question consists, A part consists 2 marks and the B part consists 3 marks. C part consists another 3 marks. D part have 2 marks. 1 mark has been allocated in part E, and part E second part you should take 2 marks altogether. This is a 13 mark question.
Okay, in part B, they are asking that the horizontal component of the velocity when the charges are ejecting or leaving the plate B is V, and we are going to apply a voltage between D and E plates, so automatically an electric field is being created there. So when the charges are leaving these two plates, they are saying that it is having a vertical component of velocity as VV, and that can be given from this equation. They are asking us electrons show that this expression is correct. We have shown that it is correct. When an electric field is applied here, what happens? The electrons are starting to move in a curved path like this. The electrons are started to move in a curved path like this, and from this one, horizontal component can be taken as VH, and the vertical component of the velocity can be taken as V, and electrons are in a curved path. Why this is happening so? When we apply an electric field here, the electric field lines are created like this. So, now as we already know, F equals QE. So, as we are taking electrons, F equals minus EE. So, the force should be to the opposite direction of the electric field. Here, this is positive, this is negative, and the electrons can be considered moving like this, or else you can take it to this direction also. That depends on how you are taking the charge of the plates. Then we'll prove this equation. To prove this equation, first of all, we have to let's discuss about the force which is applying on these electrons. The electric field force is acting on the electrons. The electric field force acts on an electron. Let's consider one electron which is moving in this path can be taken as Fe. So from the equation we can take the magnitude of electric force equals to charge of electron into electric field strength. That is the first equation. Then we can apply Newton's second law for the vertical motion of this electron. Apply Newton's second law for the vertical motion. of electron. So that one gives us this Newton's law applications gives us, we are going to apply F equals ma to this direction, vertical direction. So F is the electric field force, vertical force is the electric field force. So Fe equals mass of the electron multiplied by the acceleration. But they have provided us the vertical velocity component parameter. So we have to write this acceleration in terms of vertical velocity. So how to write it? Acceleration equals delta V over delta T. Here we can take initially VV was 0, and in the considering moment vertical component of the velocity is VV. So we can consider this one as P, this one as Q. For P and Q stages, acceleration equals VV minus 0 divided by delta T. Then let's take this one, the initial stage of the motion before entering to the electric field. Here what happens? Before enters to the electric field, horizontal component of the velocity is V, and there is no vertical component of the velocity. And when it ejects from the electric field, what happens? It exists a horizontal component of velocity as well as the vertical component of velocity. And let's take this deviation angle as theta. Then this is how to apply the Newton's second law for this motion. Electric Fe is the vertical force on electron. Then we can solve F equals ma like this. Fe equals mass into acceleration. Mass into vertical acceleration. Here acceleration parameter is not provided. Only these parameters are provided. So we have to write acceleration in terms of VV. So how to write it? Acceleration equals delta V, difference of velocity divided by the difference of time. Let's assume delta T time difference was taken from this electron to move from here to initial state to final state. Then delta V means V vertical final minus V vertical initial divided by delta T. So V vertical final is VV, and initially it don't have a vertical motion. It's just doing a linear motion straight forward the stream. So it don't have a, its initial vertical velocity is 0. So VV divided by delta T, it becomes VV divided by delta T. So FE can be written as M VV divided by delta T. Then we have to find FE is EE. FE can be written in terms of EE. Then we have to solve this delta T. We have to find this delta T in terms of the provided parameter. For this motion, for the horizontal motion, as the key point 3, we can find a relationship for delta T. For the horizontal motion, of electron, final horizontal velocity equals V, because there is no acceleration to horizontal direction. Then we can apply S equals ut, S equals u delta t for delta S equals u delta t equation for the linear motion. From that one we can take V L equals V into delta t, such that delta t equals L divided by V. So this is first equation. This is second. This can be taken as second equation. Application of second equation to first equation from first and second equations, we can write that EE, from this one we can just subject V equals EE M into delta T. Then EE M delta T is equals L divided by T. So the given equation was proved. This is how the marks are being allocated. That's a 3-mark question for taking to showing the electric force field as Fe equals E 1 mark. Second key point is the applying Newton's second law for this motion. So that for that 2 marks, and here after it comes the key point 3, finding a relationship for delta T and applying that one. For this step 1 mark, altogether 3 marks are there.